remind you that the main aspect of concentration that you need to be familiar with is the concept of molarity. And molarity or molarity is defined as the number of moles of solute in 1 liter of total solution, meaning it includes the moles per 1 liter of solution. Now, some of these things may sound redundant to you or things that you already know, but a solution in its simplest form is a solvent, only one solvent, plus one or more solutes. So you can actually have a solution in which you have 2 solutes. The first one that comes to mind is air. Air is a solution, it's a gas, but it's a solution of nitrogen, oxygen, carbon dioxide, and many other gases. The one present in the largest amount is always the solvent. In the case of air, nitrogen is the solvent, the other gases are the solutes. In the case of aqueous solutions, water is going to be the solvent, and everything else is going to be the solutes. So, but for the purposes of biochemistry, the number of solutes is often just 1 or 2, and the solution is composed of only those 1 or 2 solutes. Now, molarity is sometimes given to you in units of molar. So, for instance, you can have a 1 molar solution, abbreviated capital M. You can have a 0.5 molar solution. Or you can be given the concentration of a solution in millimolar. So let's say 500 millimolar. Or even in micromolar. Let's say 500 micromolar. The M, the capital M, still remains moles per liter. Of course, the little m here means that you're going to be modifying the moles per liter, and you're going to have millimoles per liter and micromoles per liter. Not per microliter or not per milliliter, but per liter. Otherwise, of course, if I change the liter to milliliter, then I have molar by simple dimensional analysis. Now, you should also visualize what we mean when we say a concentrated solution versus when we say a diluted solution. So a diluted solution is going to have less solute per the same volume as a concentrated solution, right? Do you mind if you get a pair of gloves? Just thank you. So for instance, if I mention to you that we have a solution of sodium chloride that is 0.1 molar, you immediately should be thinking, oh, so that means that in 1 liter I have 0.1 moles of NaCl. And if I have a solution that is 1.5 molar, I have a lot more sodium chloride than in this solution. So I have 1.5 moles of NaCl per liter. So again, this is a quick review of concentration. Now, how do you prepare a molar solution in the lab? Well, it's actually quite straightforward if you know what you are doing. So let's say that you need to prepare a buffer that in its ingredient composition or list tells you that you need 0.25 molar NaCl solution. Never mind the other components, we're just going to concentrate on this one. Each solute is considered separately. And let's say that we need to prepare 500 milliliters of that solution. So what do we need to know? Well, we need to know, of course, that the idea of mole relates to the molar mass of the compound. We need to know that the molar mass of the compound can be obtained by looking at the periodic table or by asking any internet search engine to give it to you. 23 and 35.5. Okay, 58.5. So I looked up the formula weight and molar mass of sodium chloride, and I know that 1 mole of NaCl weighs 58.5 grams. So after all, if you remember, the molar mass is defined in units of grams per mole. So 58.5 grams per 1 mole of sodium chloride. Now, in this case, what I need is 0.25 moles, not 1 mole. And moreover, I need that in only half a liter, not in a whole liter. So how do I proceed about that? Well, if I were to multiply this amount, which is 1 mole, by 0.25, I would get the number of moles that I need to make a 0.25 molar solution, but I would get it for 1 liter. Then I would have to, of course, divide by, in this case, by 2 or multiply by 0.5 to get the proper amount to mix with that half a liter of in this case, water. But essentially, that's the procedure. So you figure out the formula weight. You figure out that you need 0.25 moles, and that you only need a half a liter of that solution. Again, this is not biochemistry. This is a quick review of Chem 101. But it's important that you understand this idea of concentration, because now we're going to move on to talking about water and the concentration of water. What do I mean by concentration of water? Well, pure water, H2O, has a concentration, and you can look up how this came about, of the following: 55.5 molar, bless you. 55.5 molar is the concentration of water in water. How concentrated is that? Well, it's hugely concentrated, because in the lab we typically deal with concentrations of 1 molar or less. Sometimes 1.5 molar, rarely more than, say, 2 molar. So 55.5 molar is a huge, huge concentration of water. This is the concentration of water in water. So water is the solute, water is the solvent. It's a little tricky to understand. But with this number, there is a very interesting property of water that can be extracted. Now let's take a look at what happens when water reacts with water. So here we have H2O reacting with H2O. And then it reaching an equilibrium with the products of that reaction. The products of the reaction are going to be H3O plus OH minus. This H3O plus is called hydronium. The hydronium ion. And is often simply written as H plus. We don't waste time and write the whole thing. But as you can see, what we are saying is that, and it makes perfect sense when you look at collision theory. So if we draw the molecule of H2O in 2 dimensions, we see that there are 2 covalent bonds joining each hydrogen to the oxygen, that there are 2 pairs of lone electrons that are non-bonding, and that is per water molecule. We also know from, I think, a previous discussion that this generates a slightly negative charge around the oxygen and a slightly positive charge around the hydrogens. And that after all, these partial positive and negative charges are responsible for hydrogen bonding. So the attraction of a negatively charged area in this water molecule feels the presence of the slightly positively charged area of this other water molecule, and they form an electrostatic attraction that we know as a hydrogen bond. Now, when you break one of these hydrogen bonds, you simply have H2O. But sometimes you actually do break a covalent bond. These collisions, these water molecules are colliding against each other, hitting each other. And on occasion, one of these hydrogens comes off and it joins the other water molecule. So this actually gets removed and added to these. Now, that happens very rarely. So this equilibrium, as written, I have exaggerated the fact that the 2 arrows, which signify a reaction that is going back and forth, are of equal length. Well, that's not really what is happening. Most of the water is water. I mean, look at the concentration of water in water. So to properly draw these, I would love to always be able to, but I forget, or I just simply don't do it, show a big arrow pointing towards the reactants and a little arrow pointing towards the products. Basically saying, okay, so the equilibrium lies way to the left of this reaction. Now, I just threw another term that you need to remember what it means, equilibrium. Every chemical reaction has something called an equilibrium constant. That equilibrium constant tells you whether the product side of the reaction is favored or the reactant side of the reaction is favored, or if they are more or less the same. And the equilibrium constant of a generic reaction, let me put it over here. If we have A reacting with B to produce C plus D, the equilibrium constant of that reaction is given by the ratio of the product of the products, concentrations that is, divided by the ratio, divided by the product of the reactants. Now there are some rules that you should remember. These things here can only be participating in the equilibrium constant if they are gases, aqueous, and that's it. Solids and liquids are not included in an equilibrium constant. So we ignore them. With that information, we're going to find out that the equilibrium constant of water is actually quite different. But that's where this is going to come from. Okay. Equilibrium constants are calculated using very sophisticated physical-chemical procedures. But they are available to you in tables, so you can look them up. You can look up the equilibrium constant of virtually almost all reactions that are important. It turns out that you can actually look up the equilibrium constant of the dissociation of water, and that actually has a very interesting value. Now, I gave you the concentration of these two species as being 55.5 molar. What is the concentration of these two at equilibrium? It turns out that the concentration of these two guys at equilibrium is 1 × 10⁻⁷ molar in pure water. When dealing with equilibrium constants, we often don't put units. I'm putting them here just because these are concentrations. But we're going to ignore them when we use equilibrium constants. So because this is a liquid, and these are both aqueous, when we calculate the equilibrium constant for water, we're going to put the product of the products divided by the product of the reactants. But the reactants are both liquid, so we don't include them. So this is going to be divided by 1. They're not included. So if we substitute the values that we know, and these are measured values, again with a very sensitive equipment, we end up having to multiply 1.0 × 10⁻⁷ by that again. And the value that we get is so special that we give it a name. Instead of the KEQ, the equilibrium constant, we call it the ion product of water, KW. So KW is going to be equal to the product of those two, which is actually 1.0 × 10⁻⁴. That's the value of the equilibrium constant of the dissociation of water. So, if you think about it, the amount of water here is 55.5 moles per liter. The amount of the products of the reaction is 0.0000345 1, 2, 3, 4, 5, 6, 7 moles per liter. So 55 almost billion, 5 billion times more concentrated the water than the ions. Nevertheless, we have actually exploited the fact that we can measure that tiny amount of the ion product of water. We can actually measure that amount, and that's where the pH scale comes from. Okay? So let me erase some of the extra stuff here, and we'll jump ahead a little bit. So essentially the Kw is defined as the concentration of, and I'm going to simplify this by just calling it H plus instead of H3O plus times the concentration of OH minus, which as you know equals 1.0 times 10 to the negative 14. In pure water, these two amounts are equal, so you can solve in reverse. You take the square root of that number and you get back the 1.0 times 10 to the negative 7. Now, pH is defined for any aqueous solution as the negative log base 10, not the base 2 or natural log, of the concentration of H plus in that solution. So that's how pH is defined. That little p means negative log of. So little p, negative log of H, there is the H. So what is the pH of pure water? You already know the answer to that question, but mathematically, in pure water, we have a negative log of 1.0 times 10 to the negative 7. And if you use the calculator right, and if you ignore the negative sign for now, you get the log of that is actually going to be negative 7. And then negative times negative is positive, so you're going to get 7. And it's important that you do know how to use your calculator. So we're going to practice a couple of problems here to make sure that your calculator is giving you the right answers. So let's do a quick problem here. Calculate the pH of a solution that has 1.3 times 10 to the negative 4 molar H plus ions. So the concentration of H plus is 1.3 times 10 to the negative 4. Well, it's actually quite straightforward in this case. We know pH equals negative log of the concentration of H plus. We know that pH is going to be equal to the negative log of this number, 1.3 times 10 to the negative 4. And that should give us an answer. Quick reminder of logarithms, and just so that you know, the log of 10 to the negative 1 is going to be 1. The log of 10 to the negative 2 is going to be 2. Well, negative 2. That's why we have the negative sign. So on and so forth. So why am I telling you that? Well, because when you do this calculation, if we ignore the 1.3, we know that the log is going to be between negative 3 and negative 5, around negative 4. The 1.3 is going to change it. It's not going to be an integer. It's going to be some other number. So, but at least it gives you a checkpoint so that if your answer is something like the pH is 10, you know you made a mistake. It cannot be 10. It's going to be somewhere between 3 and 5 based on that. So what do you guys get?
2.88.
Okay, so if we do it to two significant digits, 2.9 you said? 3.9.
3.9.
Okay, the pH is going to be 3.9. And as you know, that is an acidic pH. So when the concentration of H plus is larger than the 10 to the negative 7, this number is more than 10 to the negative 7, then the pH is going to be acidic. When it's exactly 10 to the negative 7, it's going to be neutral. When the concentration is less than 10 to the negative 7, let's say 10 to the negative 9 or 10 to the negative 12, then it's going to be basic. So we're going to list them here. So pH equals negative log of the concentration of H plus. There's another scale that we don't use called the pOH, which, as you can imagine, is going to be the negative log of the concentration of OH. Because the Kw is 1.0 times 10 to the negative 14, we actually can get the pKw, and it's going to be, of course, equal to the negative log of the Kw, and that's going to be 14. Because it's a constant. These guys can change, but that one doesn't. So from these, we get this equation, pH plus pOH always equals 14. You can actually get the concentration of H plus from the pH by raising 10 to the negative pH. And you can get the concentration of OH by raising 10 to the negative pOH. And then, just so that we have everything that we need, the Kw equals the concentration of H plus times OH minus, which equals 1.0 times 10 to the negative 14. With these equations, we can answer some problems in a number of different ways. So for instance, what if I were to ask you, calculate the pH of a solution that has a concentration of 2.5 times 10 to the negative 3 OH minus. So this time, you can do it on a number of different ways. And, Leave it up to you right now to decide which way you want to go. Any suggestions? How do we answer that question?
We could find the pH.
Okay, so let's do it that one way. Number one, find pOH. Perfect. So pOH equals negative log of 2.5 times 10 to the negative 3. Right? What do we get? What is the negative log of 2.5 times 10 to the negative 3? 2.6. Do I have a confirmation from somebody else? So we need at least two answers that match to make sure that we are getting this right. I'm trying to start Google and it's not. Oh, there it goes. You got 2.6? Okay, perfect. So that gives us 2 in agreement. So now what do we do? What would be step 2? Can we now find the pH?
Yes.
Yes, we can. How?
It is the pH plus pOH equal 14.
Exactly. So find pH, and we're going to say pH plus pOH equals 14. pH equals 14 minus pOH. And then we're going to say pH equals, what is it, 11.4? 11.4. So that's a very basic solution. It is solid. So let's talk about acid and base. And there are several definitions, of course, of what is an acid and what is a base. But the one useful to biochemists is the so-called Bronsted